From the shining moon visible every night in the sky to the distant black holes placed at every galaxy's center, James Webb shed light on the wonders of the universe. It's delivering on that promise, fueling new discoveries, as well as returning more spectacular views of the universe around us. And one of its most revolutionary achievements is the observation of some of the most distant galaxies ever seen. However, as the earliest and most distant galaxies ever seen, it is also one of the most enigmatic. Worse, the mysteries surrounding the farthest ever have exacerbated the ongoing crisis in cosmology. Join us as we dig deep into how James Webb's newest discovery just stunned everyone. The Big Bang Theory is our general picture of the history of the universe. This model, initially developed in the early 20th century, has survived a battery of observational tests and is extremely good at explaining a variety of cosmological observations, including the redshifting of light from distant galaxies, the appearance of leftover radiation in the form of the cosmic microwave background, the abundances of light elements, and the evolution of galaxies and larger structures. The Big Bang tells us that at some point in the distant past, the universe was hotter, denser, and expanding much more rapidly than it is today. The stars and galaxies we see throughout the universe in all directions only exist as they do because the universe has expanded and cooled, allowing gravitation to pull matter into clumps. Over billions of years, gravitational growth has fueled generations of stars and the formation of galaxies, leading to the universe we see today. Everywhere we look, in all directions, we see a universe that tells us the same cosmic story. But part of that story is the fact that the farther away we look, the farther we're looking back in time. However, because light doesn't travel instantly, but rather moves at about 300 million meters per second in a vacuum, we don't see those galaxies as they are today, but as they were billions of years ago. Moreover, our universe is estimated to be 13.8 billion years old. So, we should assume that the most distant galaxy we could ever hope to see is no more than 13.8 billion light-years away. 1 light-years is the distance light travels in a year. That point should be a cosmological horizon of sorts, beyond which no telescope should be able to see. And because nothing can travel through space faster than c, that means there should be no way a galaxy further than 13.8 billion light-years away and getting more distant all the time could affect Earth, right? Wrong. If only the universe were that simple. A cosmological horizon, in fact, is a maximum distance from which one could possibly retrieve information, and according to Jake Helton, a University of Arizona astronomer, who is also part of the JWST Advanced Deep Extragalactic Survey, or JD's team, there are a few different cosmological horizons, which have different definitions and depend on various cosmological quantities. The most relevant here is the cosmological horizon, which is the maximum distance from which light could have traveled to us in the age of the universe. This defines the edge of the observable cosmos. In March of 2024, JD's scientists revealed the powerful telescope had spotted JD's GS Z14-0, the most distant and early galaxy humanity has ever seen. However, the paradox is that JD's GS Z14-0 is located about 33.8 billion light-years away. How can we see light from an object so distant the universe isn't old enough to have allowed it to have reached us? Doesn't JD's GS Z14-0's position 33.8 billion light-years away mean we see it as it was 33.8 billion years ago, something that would surely challenge the estimation of the age of the universe? Not so. Again, this is evidence that the universe has a way of turning sensible and logical conclusions on their heads. If the universe would just sit still, then light from a galaxy 33.8 billion light-years away would take 33.8 billion years to reach us, and that would be that. But in the early 1900s, Edwin Hubble found that distant galaxies appeared to be receding away from each other, and the further apart they were, the faster they were going. In other words, the universe isn't static, it is expanding. This was further complicated in 1998 as the 20th century drew to a close when two separate teams of astronomers observed that not only is the universe expanding, but that expansion is also accelerating. The force responsible is a mystery, but it has been given the placeholder name of dark energy. There are two major and distinct periods of expansion over the 13.8 billion year history of the universe. The first is an initial period of rapid cosmic inflation that is now commonly called the Big Bang. This inflationary epoch saw the volume of the cosmos increase by a factor of 10 to the power of 26. That's 10 followed by 25 zeros. That is equivalent to your fingernail going from growing at 1 nanometer per second to suddenly growing 10.6 light years, or 62 trillion miles long. At this time, the universe was dominated by energy, and this period is known as the energy-dominated epoch. This was followed by a matter-dominated epoch beginning 47,000 years after the Big Bang. Eventually, universal expansion allowed the cosmos to cool enough to allow protons to form from quarks and gluons, and then protons to bond with electrons to form the first atoms of hydrogen, which formed the first stars and galaxies. During this period, the Big Bang-driven expansion of the universe slowed to a near halt. The matter-dominated epoch came to a surprising end when the universe was just under 10 billion years old. At this time, the universe suddenly began to expand rapidly yet again. Plus, that expansion got faster and faster, and even continues to accelerate today. This third significant period of the universe is called the dark energy-dominated epoch. It's the epoch we're currently in. Thanks to these periods of expansion of the universe, the light from JADES GS Z14-0 has only actually been traveling to James Webb and Earth for 13.5 billion years, despite its source now being much more distant than 13.5 billion light-years away. That means the Webb telescope sees JADES GS Z14-0 as it was 300 million years after the Big Bang. Without the expansion of the universe, JADES GS Z14-0 would still be around 13.5 billion light-years away, though it would have still experienced smaller local motions that could have moved it closer together or further from nearby galaxies. But such galactic movement would have been nowhere near the kind caused by the expansion of the universe. According to Helton, the cosmological horizon, or the photon horizon, is a sphere with a boundary around 46.1 billion light-years away, a figure dictated by the universe's expansion. This is the actual horizon beyond which we shouldn't be able to see a galaxy. The galaxy JADES GS Z14-0 is indeed within that horizon. To avoid confusion, astronomers actually use two distance measurement scales: a co-moving distance that eliminates the expansion of the universe as a factor, and a proper distance that includes it. That means the co-moving distance of JADES GS Z14-0 is 13.5 billion light-years, while its proper distance is 33.8 billion light-years. But JADES GS Z14-0 and other distant and ancient galaxies won't always be visible. The fact that the JWST can see JADES GS Z14-0 means it was once causally connected to Earth and our local universe. In other words, it was possible for a signal from JADES GS Z14-0 to reach us in the Milky Way. Thus, a cause in this galaxy that existed at the dawn of time could have an effect in our galaxy in this modern epoch of the cosmos. Any observable galaxy must be within the particle horizon and must have been causally connected with us at some point in the history of the universe, Helton said. This isn't the case anymore, however. Galaxies like JADES GS Z14-0 and the other JADES discovered galaxies are now so distant and are driven away from us so rapidly, thanks to dark energy, that no signal from them sent today could ever reach us. That's because the photon horizon moves away from us at the speed of light. But for really distant objects, The space between the Milky Way and those galaxies is expanding faster than the speed of light. This might seem implausible, as Albert Einstein's theory of special relativity sets the speed of light as a universal speed limit. However, that is a rule for objects with mass moving through space, not a rule for the very fabric of space itself. In around 2 trillion years after Earth and humanity are long gone, the expansion of the universe means that whatever intelligent species replaces us in the Milky Way, if one ever does, will be unable to see any galaxies that exist beyond our local group, which has a diameter of around 10 million light-years. It is a sobering thought, and it means humanity lives at a unique point in the history of the universe at which the most distant galaxies are still within our view. And we are capable of knowing more about the universe and its origins than any intelligent life that may follow us if we use James Webb to fully exploit this cosmic privilege. Put simply, James Webb is giving us a new dictionary to translate the language of the early universe. But as James Webb has continued to fuel new discoveries, as well as returning more spectacular views of the universe around us, it has upended cosmology as much as some scientists feared. For instance, early galaxies captured by James Webb themselves, such as JD's GS ZZ14-0, are quite distinct. For starters, it's extremely bright, being the third most luminous distant galaxy out of hundreds we've imaged so far. And it's big enough that it's not possible for all its light to be originating from the core. That rules out the possibility that what we're looking at is a blurred view of an active galactic nucleus powered by a supermassive black hole feeding on material. Instead, much of the light we're looking at seems to have originated in the stars of JD's ZZ14-0. Most of those stars are young, and there seems to be very little of the dust that characterizes modern galaxies. The researchers estimate that star formation started at least 100 million years earlier, meaning just 200 million years after the Big Bang, and continued at a rapid pace in the intervening time. Combined with earlier data, the researchers write that this confirms that bright and massive galaxies existed already only 300 million years after the Big Bang, and their number density is more than 10 times higher than extrapolations based on pre-James Webb observations. In other words, there were a lot more galaxies around in the early universe than we thought, which could pose some problems for our understanding of the universe's contents and their evolution. As a result, many scientists immediately cue the headlines proclaiming the death of the Big Bang theory. In particular, the independent scientist Eric Lerner, who has long advocated for an alternative model of cosmology, wrote an article titled "The Big Bang Didn't Happen." His piece went viral. And others who endorse either creationism or intelligent design are also using these reports to claim the same thing. Among other things, Lerner claims that the galaxies captured by the James Webb telescope are too old and too numerous to be compatible with the Big Bang hypothesis, on the grounds that it is impossible for galaxies as large as the Milky Way to form in just a few 100 million years. The evidence, as Lerner says, points to a non-expanding universe, not an expanding one. That would mean big trouble for the Big Bang theory if it were true, but the truth is more interesting than the hype. The Big Bang, which took place almost 13.8 billion years ago, has not been disproven by the James Webb telescope. Instead, its images have given scientists a chance to rethink how the cosmos has evolved. On the other hand, those stories of dethrone the Big Bang theory left out a crucial detail. Astronomers estimated the redshift of those galaxies through a technique known as photometry, which is incredibly uncertain. A full evaluation of the ability of those galaxies to break cosmology would have to wait for a more precise measurement of their redshift, and hence their age. When those more precise measurements finally came a few months later, those galaxies turned from record-shattering to just normal galaxies. For example, one galaxy's redshift was revised from over 16 to just 4.9, moving its age from 240 million years after the Big Bang to well over a billion years. That's more than enough time for the normal Big Bang theory to explain their sizes and shapes. But along with those less exciting revisions came some new confirmed redshifts of other galaxies, including JD's GS Z14-0, the current most distant known galaxy, with a redshift of 14.32. This galaxy was alive and well when the cosmos was just 290 million years old. Astronomers fully expected galaxies to exist 290 million years after the Big Bang. That's why they built James Webb. And as galaxies go, Jade's GS Z14-0 is certainly a juvenile. It's only 1,600 light-years across, compared with the Milky Way's 100,000 light-years. But interestingly, the galaxy is rather bright and full of stars, not enough to outright break cosmology, but enough to open up some questions about the origins and development of the first galaxies to appear in the universe. It's quite possible that the Big Bang theory is wrong. Scientists must maintain the mental discipline to admit the possibility. But with such a wealth of evidence behind it, the Big Bang is unlikely to be unseeded from a single observation. And it's worth reiterating that James Webb is doing exactly what we designed and built it to do: answer some major lingering questions about how the first stars and galaxies appeared. It's entirely possible that cosmologists will be able to explain the appearance of galaxies, like JD's GS Z14-0, within the framework of the Big Bang without having to make any major revisions. For example, large black holes may have appeared before these galaxies did, and their superpowered gravitational attraction may have triggered bright bursts of star formation. Or perhaps supernova feedback and other mechanisms caused the first galaxies to be richer with stars than present-day galaxies, making those early galaxies appear mighty despite their small size. Or maybe our initial observations are biased toward these small but bright outliers, and further campaigns will reveal larger populations of more mundane galaxies, thus reducing the tension with galaxy formation models. And lastly, perhaps we need to add some new ingredient to the universe, like allowing for dark energy to evolve with time, to produce these kinds of galaxies at such early times. This is exciting enough on its own, without the need to upend the Big Bang as we know it. There are more than enough mysteries and hidden corners within the universe to keep astronomers up at night, wondering about the possibilities, and up in the morning to keep working on how to solve them. Either way, when we're studying the universe itself, that is, asking it questions about itself in a scientific fashion, and then listening to whatever answers it provides to our various experimental and observational questions, we're engaging in what's known as basic research. For most of us who do it, the motivation to engage in this sort of basic, fundamental research is anything but practical. We do it because we're curious about what's not yet known, and the only way to find out what's beyond the known frontiers is to investigate the universe in a scientific fashion. If having our curiosities sated were the only spoils of these pursuits, it might be easy to craft an argument that it's a frivolous waste of resources to spend so many of our collective resources on an endeavor that has no practical application to the substantial problems we face in society. Simply gaining knowledge for knowledge's own sake, although that might be an intellectually noble way to spend one's time, isn't going to help humanity in either the short term or long term. At least, that's the common argument that people make against the value of basic research with no foreseeable applications. But when people apply themselves to the challenges of exploring space, they make discoveries that can help the world in other ways too. Studying how we might grow food in orbit or on Mars yields insights into growing food in extreme conditions on Earth, generating knowledge that can help mitigate the impacts of climate change. Medical research conducted on the International Space Station helps us understand the human body in new ways, helping save lives and improve quality of life. More important, by studying alien worlds, such as Venus, Mars, or Saturn's moon Titan, we can place our own world in context. The exploration of the solar system is focused on understanding the Earth's relationship with the other planets, essential stepping stones for exploring the wider universe. While space may hold many wonders and explanations of how the universe was formed or how it works, it also holds dangers. The chance of a large asteroid or comet hitting the Earth is small, but given time, it will happen. Some explanations for extinctions and evolution include strikes by asteroids or comets. Our technology is reaching the point where we can detect such a threat and might be able to do something about it. The dangers exist, and knowledge can allow us as a species to survive. Without the ability to reach out across space, the chance to save ourselves might not exist. Earth is the only planet known to sustain life, but our ability to adapt could eventually allow us to inhabit other planets and moons. Our lifestyles would be different, but human life and cultures have adapted in the past and surely could in the future. Space allows us to expand and succeed. In addition, space is inspiring. Not every child who dreams of becoming an astronaut will get that opportunity. This is a sad truth that many of us know from experience. But to be inspired to aim for something so grand gives kids the motivation to study hard and gain skills in science, engineering, medicine, or other fields that benefit humanity and directly help overcome problems that we face as a species. And inspiration isn't just for kids. When we marvel at the beauty of Jupiter's clouds or the mystery of Enceladus's oceans, we get an opportunity to appreciate the wonder and majesty of this cosmos that we inhabit. The idea that life might exist elsewhere in the universe reminds us that we might not be the only planet struggling to achieve balance, justice, and sustainability. And even in the bleakest of times, there's something beautiful about still striving to achieve something great and discover something that could change how we see ourselves and our cosmos forever. There's no denying that there are many important issues facing humanity that need fixing. But to deal with those problems doesn't mean we have to stop looking up, stop exploring, and stop making discoveries. Human civilization has astonishing capacity, and we can do more than one important thing at a time. If someone thinks that a particular issue should get more attention and investment, they can and should advocate for that. The problems we face don't persist because we're spending money on space science and exploration, and there's no reason to pit our aspirations against one another. Such an effort is coming. It's big, it's powerful, and it's going to change everything. If this sounds like the tagline from a Godzilla movie, then you have the right scope in mind. But I'm talking about a telescope, a very big telescope. Actually, it's the extremely large telescope, and it's only a few years away from competition. The first thing to understand about telescopes is that size is everything. Many people think the purpose of a telescope is to magnify distant objects, but the first order of business is actually to collect light. The farther away a light source is from us, the dimmer it appears, and its brightness falls off with distance squared. For instance, if you move a light bulb 10 times away, it will appear 100 times fainter. To help us see faraway light sources, telescopes act as a kind of light bucket. They collect as many photons as possible from distant objects to give us the all-important signal that can stand out against background noise. Why does size matter then? The light-collecting power of a telescope is the square of its collecting surface. If we use mirrors, as all modern telescopes do, then a telescope built from a 10-meter mirror will collect 100 times as much light as a 1-meter instrument. As such, astronomers want a telescope with the biggest mirror possible. What is the biggest mirror possible? That's the question the extremely large telescope will answer. For the last 30 or so years, the big research-class telescopes had mirrors in the 10-meter range. That's roughly 33 feet for those of us stuck in U.S. units. These include the two 10-meter Keck instruments on top of Mauna Kea in Hawaii. Building a movable frame that can hold a 10-meter mirror and then constructing an observatory dome around the whole thing was an amazing engineering task. However, the extremely large telescope takes amazing engineering to an entirely new level. The mirrors on the extremely large telescope will be almost 40 meters across, but they have to be built first. They must then be supported by a movable frame with a size stretching across an entire football field. Of course, a telescope is not just a primary mirror. There will also be a secondary mirror positioned above it that collects the light bouncing off the giant primary before redirecting it down to the various instruments. And the entire structure has to fit within an observatory dome to protect it from the elements, including the wind, which could shake the whole thing to uselessness. Unsurprisingly, the extremely large telescope dome will be the biggest ever built, coming in at 74 meters high and 86 meters across. The total weight of both the telescope and dome, 9,000 tons. What's more, the extremely large telescope is designed to work in both optical and near-infrared wavelengths of light. Getting telescopes high above the atmosphere is always job number one for site planning, but because infrared light gets absorbed by water vapor, you want the location to be high and dry. That's why this extreme engineering project is being carried out on Cerro Armazones, a mountain in Chile's Atacama Desert, one of the driest places in the world. Cerro Armazones once stood 3,064 meters above sea level, but in June 2014, the top was blasted away to level the mountaintop for construction, shaving 18 meters off its height. Cerro Armazones was selected as the location for the extremely large telescope because of its excellent atmospheric and climatic conditions. The sky above Cerro Armazones is extremely dry. There is very low precipitable water vapor content, resulting in an annual rainfall of just 10 centimeters. Because it is far from towns and cities, Cerro Armazones is also exceptionally dark, with the only light pollution being on the northwestern horizon from the coastal city of Antofagasta, 36 kilometers away, and a few very distant mines. When you consider what's being built and where it's being built, the extremely large telescope is nothing short of an engineering marvel. So, what will come of all this? The answer is simple: a game-changing astronomical instrument. The extremely large telescope will have a light-collecting power that's 100 million times better than the human eye and more than 10 times better than the best telescopes that exist today. That capacity means questions currently out of reach will get answers, or at least much better answers than we can get now. There are 8 main science areas that the extremely large telescope will focus on: the solar system, exoplanets, stars, black holes, galaxies, cosmology and dark matter, fundamental physics, and unexpected discoveries. First up is the extremely large telescope's planned studies of the solar system. The telescope will probe the atmospheres of the gas giants, as well as study volcanism and cryovolcanism on the moons of Jupiter and Saturn. It will also capture the spectra of asteroids in the asteroid belt and distant frozen objects in the Kuiper belt. The extremely large telescope will also look at exoplanets. In addition to having a large aperture for imaging rocky planets in the habitable zones of their stars, it will spectroscopically characterize the atmospheres of these potentially habitable exoplanets, particularly those set to be discovered by the European Space Agency's PLATO, or Planetary Transits and Oscillations of Stars, mission, which is scheduled to launch in 2026. The extremely large telescope's Armazones High Dispersion Echelle Spectrograph, also known as ANDES, will be capable of detecting biosignatures, water vapor, oxygen, and methane, in the atmospheres of such worlds. The telescope will also be adept at studying planet formation in dusty disks around young stars and, with its mid-infrared imager and spectrograph, or METIS, could even detect moons forming around planets. In addition, the ELT will probe star formation, not only in the present but also in the past, chronicling the star-forming history of the universe. The extremely large telescope website describes such measurements as critical to understanding the link between dark matter and visible matter, since dark matter draws in visible matter, enabling it to form stars faster. The telescope will also chase down supernovas and the sources of gamma-ray bursts, as well as study the chemistry in the form of heavy elements created by these stellar explosions. Supernovas and gamma-ray bursts are thought to form black holes. These are described as stellar mass black holes, and the extremely large telescope will study the population of these black holes, as well as intermediate mass black holes with between 100 and 10,000 times the mass of the Sun, and supermassive black holes with millions or billions of solar masses found at the centers of galaxies, including the Milky Way. In particular, the telescope will seek to characterize Sagittarius A, the supermassive black hole at the heart of our galaxy, using the orbits of stars that pass very close to the black hole. One key instrument on the telescope to help it achieve these observations of black holes will be the high angular resolution monolithic optical and near-infrared integral field spectrograph, or HARMONY for short. Black holes play a key role in the evolution of their host galaxies. As with star formation, the extremely large telescope will also study the evolution of galaxies throughout cosmic history, tracking down some of the extremely distant galaxies that the James Webb Space Telescope is finding, and that existed just a few 100 million years after the Big Bang. It will also explore the cores of galaxies, not just the black holes, but also their nuclear star clusters, which are dense agglomerations of stars that surround the black hole. On the grandest scale, there is the cosmology of our seemingly dark universe, one dominated by dark matter and especially by dark energy, which may require new fundamental physics to explain them. The extremely high-resolution observations made by the extremely large telescope will be able to detect behavior in the expansion of the universe or in the light of stars and galaxies that might hint at new fundamental physics or evidence of changes in the behavior of the fundamental constants of nature, such as the speed of light and the proton-to-electron mass ratio. A lot of the extremely large telescope's cosmological studies will be conducted with Andes. Finally, the telescope may make many unexpected discoveries. It will be capable of seeing things no human has ever seen and of observing familiar objects in a level of detail never achieved. When scientists do this, they often discover new things that nobody ever expected, like the discovery of dark energy by astronomers using the Hubble Space Telescope in 1998 and the finding of hot Jupiter exoplanets in 1995. Who knows what the extremely large telescope will discover? That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.